Our galaxy, the Milky Way, is home to billions of stars. These stars vary greatly in size, age, and composition, creating a diverse and dynamic celestial landscape. Some of these stars are quite young, just a few million years old. These youthful stars are often found in vibrant clusters and nebulae, where star formation is actively taking place. Others, however, are incredibly ancient, reaching back billions of years. These stars have witnessed the galaxy's evolution over eons, serving as silent observers of cosmic history. These ancient giants, as we call them, hold secrets to the Milky Way's formation and the early universe. Their long lifespans and stable conditions make them perfect candidates for studying the past. They are like time capsules, offering glimpses into a time long before our sun was even born. By examining these stars, astronomers can piece together the story of our galaxy's origins. One defining characteristic of these ancient stars is their age. They have existed for nearly as long as the universe itself, providing a direct link to the conditions that prevailed shortly after the Big Bang. They formed around 12 billion years ago, a mere whisper after the Big Bang. This makes them some of the oldest known objects in the universe, predating even the formation of the Milky Way. Another key feature is their composition. By analyzing the light from these stars, scientists can determine the elements they contain, revealing important clues about the early universe. These stars are incredibly metal poor. In other words, they contain very few elements heavier than hydrogen and helium, which were the primary components of the early universe. In astronomy, metals refer to elements heavier than hydrogen and helium. The scarcity of these heavier elements in ancient stars indicates that they formed before these elements became more abundant in the universe. The early universe was primarily composed of these lighter elements, so stars formed later with more metals are considered more enriched. This enrichment process occurred as successive generations of stars created and dispersed heavier elements. These ancient metal-poor stars are not just fascinating relics of the past. They are living records of the universe's formative years, providing a window into the processes that shaped the cosmos. They are crucial to our understanding of how galaxies form and evolve. By studying these stars, astronomers can trace the history of star formation and the chemical evolution of galaxies. By studying these stellar ancients, we gain insights into the conditions of the early universe and the processes that led to the Milky Way we observe today. Their light carries information from a time when the universe was still young and chaotic. Their existence and characteristics provide valuable clues about the dramatic events that shaped our galaxy. From supernova explosions to galactic collisions, these ancient stars have witnessed it all, helping us understand the forces that have sculpted the Milky Way into its current form. Imagine looking at a photograph from your childhood. It's a simple piece of paper, yet it holds a world of memories. The laughter, the innocence, the moments that shaped who you are today. It captures a moment in time, preserving details about your younger self and the world around you. Each photograph is a portal to the past, a way to relive those precious moments. Ancient stars serve a similar purpose, acting as cosmic snapshots of the early universe. They are the universe's own family album, filled with stories of creation and transformation. Their low metal content is a telltale sign of their age and origins. These stars are like the sepia-toned photographs of the cosmos, revealing a time when the universe was young and still finding its form. In the aftermath of the Big Bang, the universe was primarily composed of hydrogen and helium. These were the building blocks of everything we see today, the raw materials from which the first stars were born. The first generation of stars formed from these primordial elements. They were the pioneers, blazing trails in the dark, empty expanse of the early universe. As these stars aged and died, they exploded as supernovae, scattering heavier elements, or metals, into space. These cataclysmic events were like cosmic fireworks, seeding the universe with the ingredients for future stars and planets. These newly synthesized metals then became incorporated into the next generation of stars. Each new star carried the legacy of its predecessors, enriched with the elements forged in the hearts of ancient stars. Consequently, stars that formed later in the universe's history tend to have a higher metallicity, meaning they contain a greater abundance of heavier elements. These stars are like the colorful, high-definition photographs of today, rich in detail and complexity. Ancient stars, on the other hand, formed before significant metal enrichment had occurred, making them remarkably metal-poor. They are the relics of a bygone era, silent witnesses to the universe's earliest days. This characteristic is a crucial clue to their age and provides a window into the chemical composition of the early universe. By studying these ancient stars, we can piece together the story of how the universe evolved from a simple mix of hydrogen and helium to the rich, diverse cosmos we see today. The birth of the Milky Way was not a peaceful event. It was a chaotic and violent process involving the merging of smaller galaxies. These mergers triggered intense bursts of star formation, giving rise to ancient stars that populate the Milky Way's halo, a vast, spherical region surrounding the galactic disk. The formation of these ancient giants was not a uniform process. Some formed within the Milky Way itself, while others originated in smaller dwarf galaxies that were later consumed by our own. These galactic mergers played a significant role in shaping the Milky Way's structure and distributing stars throughout its halo. Evidence suggests that a significant fraction of these ancient stars were not born within the Milky Way, but were acquired through galactic cannibalism. These stars often exhibit unusual orbits, moving in the opposite direction to the majority of stars in the Milky Way's disk. These retrograde orbits are a telltale sign of their extragalactic origins and provide valuable insights into the Milky Way's tumultuous past. In the Milky Way, most stars orbit the galactic center in a relatively orderly fashion, moving in the same direction. This orderly motion is a result of the galaxy's formation and the gravitational forces that have shaped it over billions of years. The majority of stars, gas, and dust in the Milky Way follow this grand spiraling dance, creating the beautiful and familiar structure of our galaxy. However, a small percentage of stars, particularly those in the galactic halo, exhibit retrograde orbits, meaning they move in the opposite direction to the majority of stars. These stars are like cosmic rebels, defying the established order and hinting at a more tumultuous past. Their unusual paths are not just random anomalies, but are clues to the dynamic and often violent history of our galaxy. This peculiar behavior is a key indicator of their origins outside the Milky Way. These stars were not born in the calm, nurturing environment of our galaxy, but were instead captured from other, smaller galaxies. Their retrograde motion is a telltale sign of their extragalactic origins, providing astronomers with valuable insights into the processes of galactic formation and evolution. Imagine a river flowing downstream. The current carries everything along in a smooth, predictable manner, much like the stars in the Milky Way's disk. Most objects in the river, like leaves or branches, will naturally drift along with the current. This is the expected behavior, mirroring the orderly motion of most stars in our galaxy. However, if you spot an object moving upstream, it's a clear sign that it didn't originate in the river itself. It stands out, drawing attention because it defies the natural flow, just like the retrograde stars in the Milky Way. Similarly, stars with retrograde orbits stand out because their motion defies the general flow of stars within the Milky Way. These stars are like cosmic detectives, helping us piece together the history of our galaxy by revealing the hidden stories of past galactic encounters. These retrograde orbits are strong evidence that these stars were once part of smaller dwarf galaxies that were captured and disrupted by the Milky Way's gravity. The gravitational forces of our galaxy tore these smaller galaxies apart, scattering their stars, and leaving behind these intriguing retrograde orbits. As these smaller galaxies fell into the Milky Way, their stars were scattered throughout the halo, some ending up with these unusual backward orbits. This scattering process is a testament to the dynamic and ever-changing nature of our galaxy, where past collisions and mergers have left their mark in the form of these retrograde stars. The presence of these retrograde stars provides compelling evidence for the Milky Way's history of galactic mergers and its role in shaping the distribution of stars within its halo. Each retrograde star is a piece of the puzzle, helping astronomers understand the complex and fascinating history of our galaxy. By studying these stars, we can learn more about the processes that have shaped the Milky Way and continue to influence its evolution.